You know, we all love Python because it's so simple. And a huge part of that is not having to constantly worry about memory. It just works, right? Well, until it suddenly doesn't. See, behind the scenes, there's this silent cleaner that's always tidying up our code, but it has one critical weakness. In this explainer, we're going to expose that weakness and get a good look at Python's garbage collector.
So, this is the big mystery we're here to solve today. You write your code, you delete your variables, and you just assume that memory gets freed up. But every now and then, some objects just refuse to die. They linger like ghosts in the machine, slowly, quietly, eating up all your resources. So why does this happen? Let's find out. Okay, here's our game plan. First, we'll uncover the one big problem that Python's main memory system just can't handle on its own. Then, we'll meet the hero that solves it, the generational garbage collector. After that, we'll learn how to actually control it, how to sidestep a really common trap, and even how to become memory detectives. And finally, you'll walk away with the golden rules to keep your apps running lean and fast. So let's get into it. What exactly is this unseen problem? Well, it all starts with Python's main strategy for memory, which is called reference counting. It's simple, it's usually really fast, but it has this one critical blind spot, and that's what creates these ghosts in our memory. The idea behind reference counting is pretty straightforward. Every object keeps a little counter of how many variables are pointing to it. When that counter hits 0, poof, Python reclaims its memory. Simple. But here's the catch. Imagine we have two objects. Let's call them A and B. We make A point to B, and then we make B point right back at A. They've created this little closed loop, see? Now, even when we're totally done with them and delete our variables, their reference counts never drop to 0. Why? Because they're still pointing at each other. They're completely unreachable from our code, but they're stuck in memory. And that, right there, is a memory leak. So to break these kinds of cycles, Python has to call in a specialist, the garbage collector, or GC. Its entire job is to hunt down and clean up these isolated little loops that reference counting misses. Now, the secret to the garbage collector's efficiency is this brilliant yet really simple idea. It's called the weak generational hypothesis. And it's based on a key observation about how we code. Most objects die young, right? In a typical program, you create things, use them for a second, and then they're gone. So why waste time checking on old, long-lived objects over and over again? It's way more efficient to focus all the cleanup effort on the newcomers. And this is how Python actually puts that idea into practice. It organizes all the objects into 3 generations. Think of generation 0 as your kitchen recycling bin. It fills up fast with new stuff, so you empty it all the time. Now, anything that survives a few of those cleanups gets promoted to generation 1. That's kind of like your curbside bin, which gets collected less often. And the really rare objects that survive even that move to generation 2. That's like long-term storage that's almost never checked. It's a super efficient tiered system. Now, this all happens automatically, which is great, but it's not some magic black box. Python actually gives us a whole toolkit to interact with the garbage collector directly. It's a built-in module called GC. Let's take a look at what's inside. You can think of this as your personal control panel. You can manually force a cleanup whenever you want with gc.collect. Or let's say you have a really performance-critical piece of code. You can just hit pause with gc.disable. And for debugging, oh man, getObjects and getStats are your best friends. They'll show you exactly what the collector is tracking and how it's performing. Okay, so as we're learning to control memory, we have to talk about a very common trap. There's this special method in Python called __del. It's often called a finalizer or destructor, and at first glance, it looks like the perfect place to put your cleanup code. But trust me, it is loaded with hidden dangers. Here's the bottom line. Del is just plain unreliable. You have zero guarantee when it'll be called, in what order it'll be called, or even if it will be called at all, especially if it's part of one of those cycles we talked about. In fact, it can actually stop the garbage collector from doing its job. The modern, safe, and correct way to do this is with a context manager. Using a with statement is the gold standard because it guarantees your cleanup code runs exactly when and how you expect it to. Okay, enough theory. Time to put on our detective hats. We know what causes leaks, and we know about the tools in our toolkit. So let's see how you'd actually hunt down a real memory leak in a running application. Does this look familiar to you? If you've ever run a web server or any kind of process that runs for a long time, you've probably seen these warning signs. The memory usage just creeps up and up and up over hours or even days. The app gets sluggish, and then eventually it just crashes.
These are the classic fingerprints of a memory leak at work. You know, trying to debug a leak by just staring at memory usage numbers feels like flying blind. It's so frustrating. But what if you could take a snapshot of your program's memory? What if you could actually see the web of connections that's keeping an object alive? Well, this is your investigative toolkit. The GC module itself can show you its garbage list. These are the things it knows are trash but for some reason can't collect. Then there's the tracemalloc module, which is fantastic. It can pinpoint the exact line of code where your memory-hungry objects are being created. But the real game changer is a library like Object Graph. It will literally draw you a map of object references, showing you the exact chain that's preventing something from being cleaned up. It's amazing. So we've gone all the way from the cause of leaks to the cure. Let's bring it all home and consolidate everything into a final set of rules for writing clean, memory-efficient Python code. All right, here are the key takeaways. First, and most importantly, trust the garbage collector. It is highly optimized, so just let it do its job. Don't try to outsmart it. Second, when you're designing your code, try to avoid those circular links in the first place. If you absolutely can't, use Python's weakref module. Third, and I'll say it one last time, avoid __del. Seriously. Use context managers. And finally, monitor your long-running applications. When you spot a problem, use the tools we've discussed to diagnose the root cause. No more guesswork.
So there you have it. Python's memory management is no longer a black box. You understand its limits, you understand its very clever solution, and now you have the tools to diagnose and fix any problem that comes up. You are in control. So the only question left is, what are you going to build with this power? Thanks for watching.